Hello everyone, welcome to my channel. Today we start another topic talking about special relativity from Albert Einstein documents. Are you ready? Let's start together. Relativity is a simple concept. It asserts that the fundamental laws of physics are the same whatever your state of motion. For the special case of observers moving at a constant velocity, this concept is pretty easy to accept. Imagine a man in an armchair at home and a woman in an airplane gliding very smoothly above. Each can pour a cup of coffee, bounce a ball, shine a flashlight, or heat a muffin in a microwave and have the same laws of physics apply. In fact, there is no way to determine which of them is in motion and which is at rest. The man in the armchair could consider himself at rest and the plane in motion. And the woman in the plane could consider herself at rest and the earth as gliding past. There is no experiment that can prove who is right. Indeed, there is no absolute right. All that can be said is that each is moving relative to the other. And of course, both are moving very rapidly relative to other planets, stars, and galaxies. The special theory of relativity that Einstein developed in 1905 applies only to this special case, hence the name. A situation in which the observers are moving at a constant velocity relative to one another uniformly in a straight line at a steady speed, referred to as an inertial reference system. It's harder to make the more general case that a person who is accelerating or turning or rotating or slamming on the brakes or moving in an arbitrary manner is not in some form of absolute motion, because coffee sloshes and balls roll away in a different manner than for people on a smoothly gliding train, plane, or planet. It would take Einstein a decade more, as we shall see, to come up with what he called a general theory of relativity, which incorporated accelerated motion into a theory of gravity and attempted to apply the concept of relativity to it. The story of relativity best begins in 1632, when Galileo articulated the principle that the laws of motion and mechanics, the laws of electromagnetism, had not yet been discovered, were the same in all constant velocity reference frames. In his dialogue concerning the two chief world systems, Galileo wanted to defend Copernicus's idea that the Earth does not rest motionless at the center of the universe with everything else revolving around it. Skeptics contended that if the Earth was moving, as Copernicus said, we'd feel it. Galileo refuted this with a brilliantly clear thought experiment about being inside the cabin of a smoothly sailing ship. Shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the little animals fly with equal speed to all sides of the cabin. The fish swim indifferently in all directions. The drops fall into the vessel beneath. And, in throwing something to your friend, you need throw it no more strongly in one direction than another, the distances being equal. Jumping with your feet together, you pass equal spaces in every direction. When you have observed all these things carefully, have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. There is no better description of relativity, or at least of how that principle applies to systems that are moving at a constant velocity relative to each other. Inside Galileo's ship, it is easy to have a conversation, because the air that carries the sound waves is moving smoothly along with the people in the chamber. Likewise, if one of Galileo's passengers dropped a pebble into a bowl of water, the ripples would emanate the same way they would if the bowl were resting on shore. That's because the water propagating the ripples is moving smoothly along with the bowl and everything else in the chamber. Sound waves and water waves are easily explained by classical mechanics. They are simply a traveling disturbance in some medium. That is why sound cannot travel through a vacuum. But it can travel through such things as air or water or metal. For example, sound waves move through room temperature air as a vibrating disturbance that compresses and rarefies the air at about 770 miles per hour. Deep inside Galileo's ship, sound and water waves behave as they do on land, because the air in the chamber and the water in the bowls are moving at the same velocity as the passengers. But now imagine that you go up on deck and look at the waves out in the ocean, or that you measure the speed of the sound waves from the horn of another boat. The speed at which these waves come toward you depends on your motion relative to the medium, the water or air, propagating them. In other words, the speed at which an ocean wave reaches you will depend on how fast you are moving through the water toward or away from the source of the wave. The speed of a sound wave relative to you will likewise depend on your motion relative to the air that's propagating the sound wave. Those relative speeds add up. Imagine that you are standing in the ocean as the waves come toward you at 10 miles per hour. If you jump on a jet ski and head directly into the waves at 40 miles per hour, you will see them moving toward you and zipping past you at a speed, relative to you, of 50 miles per hour. Scientists found themselves unable to explain electromagnetism using the Newtonian mechanical view of nature, he said. And this led to a fundamental dualism which in the long run was insupportable. Einstein's road to relativity. A new idea comes suddenly and in a rather intuitive way, Einstein once said. But, he hastened to add, intuition is nothing but the outcome of earlier intellectual experience. Einstein's discovery of special relativity involved an intuition based on a decade of intellectual as well as personal experiences. The most important and obvious, I think, was his deep understanding and knowledge of theoretical physics. He was also helped by his ability to visualize thought experiments, which had been encouraged by his education in Aarau. Also, there was his grounding in philosophy. From Hume and Mach, he had developed a skepticism about things that could not be observed. And this skepticism was enhanced by his innate rebellious tendency to question authority. Also part of the mix, and probably reinforcing his ability to both visualize physical situations and to cut to the heart of concepts, was the technological backdrop of his life, helping his uncle, Jacob, to refine the moving coils and magnets in a generator. Working in a patent office that was being flooded with applications for new methods of coordinating clocks. Having a boss who encouraged him to apply his skepticism. Living near the clock tower and train station and just above the telegraph office in Bern, just as Europe was using electrical signals to synchronize clocks within time zones. And having as a sounding board his engineer friend Michel Bessot, who worked with him at the patent office, examining electromechanical devices. The ranking of these influences is, of course, a subjective judgment. After all, even Einstein himself could not be sure how the process unfolded. It is not easy to talk about how I arrived at the theory of relativity, he said. There were so many hidden complexities to motivate my thought. One thing we can note with some confidence is Einstein's main starting point. He repeatedly said that his path toward the theory of relativity began with his thought. Experiment at age 16 about what it would be like to ride at the speed of light alongside a light beam. This produced a paradox, he said, and it troubled him for the next 10 years. If I pursue a beam of light with a velocity c, velocity of light in a vacuum, I should observe such a beam of light as an electromagnetic field at rest though spatially oscillating. There seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations. From the very beginning it appeared to me intuitively clear that, judged from the standpoint of such an observer, everything would have to happen according to the same laws as for an observer who, relative to the Earth, was at rest. For how should the first observer know or be able to determine that he is in a state of fast uniform motion? One sees in this paradox the germ of the special relativity theory is already contained. This thought experiment did not necessarily undermine the ether theory of light waves. An ether theorist could imagine a frozen light beam. But it violated Einstein's intuition that the laws of optics should obey the principle of relativity. In other words, Maxwell's equations, which specify the speed of light, should be the same for all observers in constant velocity motion. The emphasis that Einstein placed on this memory indicates that the idea of a frozen light beam or frozen electromagnetic waves seemed instinctively wrong to him. In addition, The thought experiment suggests that he sensed a conflict between Newton's laws of mechanics and the constancy of the speed of light in Maxwell's equations. All of this instilled in him a state of psychic tension that he found deeply unnerving. At the very beginning, when the special theory of relativity began to germinate in me, I was visited by all sorts of nervous conflicts, he later recalled. When young, I used to go away for weeks in a state of confusion. There was also a more specific asymmetry that began to bother him. When a magnet moves relative to a wire loop, an electric current is produced. As Einstein knew from his experience with his family's generators, the amount of this electric current is exactly the same whether the magnet is moving while the coil seems to be sitting still, or the coil is moving while the magnet seems to be sitting still. He also had studied an 1894 book by August Foppel, Introduction to Maxwell's Theory of Electricity. It had a section specifically on the electrodynamics of moving conductors that questioned whether, when induction occurs, there should be any distinction between whether the magnet or the conducting coil is said to be in motion. But according to the Maxwell-Lorentz theory, Einstein recalled, the theoretical interpretation of the phenomenon is very different for the two cases. In the first case, Faraday's law of induction said that the motion of the magnet through the ether created an electric field. In the second case, Lorentz's force law said a current was created by the motion of the conducting coil through the magnetic field. The idea that these two cases should essentially be different was unbearable to me, Einstein said. Einstein had been wrestling for years with the concept of the ether, which theoretically determined the definition of at rest in these electrical induction theories. As a student at the Zurich Polytechnic in 1899, he had written to Maliva Mari that the introduction of the term ether into theories of electricity has led to the conception of a medium whose motion can be described without, I believe, being able to ascribe physical meaning to it. Yet that very month he was on vacation in Aarau working with a teacher at his old school on ways to detect the ether. I had a good idea for investigating the way in which a body's relative motion with respect to the ether affects the velocity of the propagation of light, he told Mari. Likewise, imagine that sound waves are coming at you from a distant boat horn, rippling through still air at 770 miles per hour toward the shore. If you jump on your jet ski and head toward the horn at 40 miles per hour, the sound waves will be moving toward you and zipping past you at a speed, relative to you, of 810 miles per hour. All of this led to a question that Einstein had been pondering since age 16, when he imagined riding alongside a light beam. Does light behave the same way? Newton had conceived of light as primarily a stream of emitted particles. But by Einstein's day, most scientists accepted the rival theory, propounded by Newton's contemporary Christian Huygens, that light should be considered a wave. A wide variety of experiments had confirmed the wave theory by the late 19th century. For example, Thomas Young did a famous experiment, now replicated by high school students, showing how light passing through two slits produces an interference pattern that resembles that of water waves going through two slits. In each case, the crests and troughs of the waves emanating from each slit reinforce each other in some places and cancel each other out in some places. James Clerk Maxwell helped to enshrine this wave theory when he successfully conjectured a connection between light, electricity, and magnetism. He came up with equations that described the behavior of electric and magnetic fields, and when they were combined they predicted electromagnetic waves. Maxwell found that these electromagnetic waves had to travel at a certain speed, approximately 186,000 miles per second. Asterisk. That was the speed that scientists had already measured for light, and it was obviously not a mere coincidence. It became clear that light was the visible manifestation of a whole spectrum of electromagnetic waves. This includes what we now call AM radio signals, with a wavelength of 300 yards, FM radio signals, 3 yards, and microwaves, 3 inches. As the wavelengths get shorter and the frequency of the wave cycles thus increases, they produce the spectrum of visible light, ranging from red, 25 millionths of an inch, to violet, 14 millionths of an inch. Even shorter wavelengths produce ultraviolet rays, X-rays, and gamma rays. When we speak of light and the speed of light, we mean all electromagnetic waves, not just the ones that are visible to our eyes. That raised some big questions. What was the medium that was propagating these waves? And their speed of 186,000 miles per second was a speed relative to what? The answer, it seemed, was that light waves are a disturbance of an unseen medium, which was called the ether, and that their speed is relative to this ether. In other words, the ether was for light waves something akin to what air was for sound waves. It appeared beyond question that light must be interpreted as a vibratory process in an elastic, inert medium filling up universal space, Einstein later noted. This ether, unfortunately, needed to have many puzzling properties. Because light from distant stars is able to reach the Earth, the ether had to pervade the entire known universe. It had to be so gossamer and, shall we say, so ethereal that it had no effect on planets and feathers floating through it. Yet it had to be stiff enough to allow a wave to vibrate through it at an enormous speed. All of this led to the great ether hunt of the late 19th century. If light was indeed a wave rippling through the ether, then you should see the waves going by you at a faster speed if you were moving through the ether toward the light source. Scientists devised all sorts of ingenious devices and experiments to detect such differences. They used a variety of suppositions of how the ether might behave. They looked for it as if it were motionless and the Earth passed freely through it. They looked for it as if the Earth dragged parts of it along in a blob, the way it does its own atmosphere. They even considered the unlikely possibility that the Earth was the only thing at rest with respect to the ether, and that everything else in the cosmos was spinning around, including the other planets, the sun, the stars, and presumably poor Copernicus in his grave. One experiment, which Einstein later called of fundamental importance in the special theory of relativity, was by the French physicist Hippolyte Fizeau, who sought to measure the speed of light in a moving medium. He split a light beam with a half-silvered angled mirror that sent one part of the beam through water in the direction of the water's flow and the other part against the flow. The two parts of the beam were then reunited. If one route took longer, then the crests and troughs of its waves would be out of sync with the waves of the other beam. The experimenters could tell if this happened by looking at the interference pattern that resulted when the waves were rejoined. A different and far more famous experiment was done in Cleveland in 1887 by Albert Michelson and Edward Morley. They built a contraption that similarly split a light beam and sent one part back and forth to a mirror at the end of an arm facing in the direction of the Earth's movement, and the other part back and forth along an arm at a 90-degree angle to it. Once again, the two parts of the beam were then rejoined and the interference pattern analyzed to see if the path that was going up against the supposed ether wind would take longer. No matter who looked, or how they looked, or what suppositions they made about the behavior of the ether, no one was able to detect the elusive substance. No matter which way anything was moving, the speed of light was observed to be exactly the same. So scientists, somewhat awkwardly, turned their attention to coming up with explanations about why the ether existed but was undetectable in any experiment. Most notably, in the early 1890s, Hendrik Lorentz, the cosmopolitan and congenial Dutch father figure of theoretical physics, and, independently, the Irish physicist George Fitzgerald came up with the hypothesis that solid objects contracted slightly when they moved through the ether. The Lorentz-Fitzgerald contraction would shorten everything, including the measuring arms used by Michelson and Morley, and it would do so by just the exact amount to make the effect of the ether on light undetectable. Einstein felt that the situation was very depressing. Thanks you guys for take your time watching this video. Have a great day.